Hello everyone and welcome to the Victoria Game Engine series. This is episode 4 and today we are going to be tackling the variant type. For those of you who are unaware of what a variant type is, it's basically a data type that can be transferred between different general types. So normally in C++, we use static typing, which means that you can only have a data type as an integer. You can't necessarily convert that to other data types such as a string. However, through the variants, we can always be constantly converting different types. We can have functions that return different values based on what we expect. And that way we have a system that has a little bit more leniency in it and perhaps will be a lot easier for some developers to use. Now, it may not be that everyone wants to use this type, which is perfectly fine because for the most part, when we are developing the engine itself, we will want to stick with our static types and we will want to stick with the general C++ programming ideas. But when we come to making our scripting in the engine itself and we actually start, creating our own games, we will want to have some variance in how we allow people to code things to have it a little bit more weakly done and a little less rigid in the static typing methods, but that can change depending on how we want to be writing our code. Now, before we add the variant type, we need to add some things to our typedefs.h, and those are a couple more types. Now, here we have them right here. So we have an int 8, an int 16, int 32, and int 64. If you watched the previous episode, or if you watch the first episode on our setup, you will know that the uint types are the unsigned versions, which means that they have no negative numbers. And it goes from 8, 16, 32, and 64 bits. And the similar thing with our signed characters. So we have 8, 16, 32, and 64-bit signed versions. These exist. You can normally, I think, use like C limits as a standard library include to get these. But in reality, you can just use these as well as your data types, and the application will run the same. Now, I haven't added it here, and it wasn't in my notes, but we will also want to add the static assertions for these. So I will just do that quickly. All right, there we go. It's now all added. And with all that out of the way, that's the only real changes we need to make here for now. Now we get to create the variant type, and it's going to be in a folder called variant. Reason being is that over the course of creating our application, we will have various different things that we'll want to include in the variant type that don't really fit in other parts of the system, and we'll keep them in the variant for this reason. And it's going to be in the variant.h file, so I'll just quickly copy and paste an if and def and define, and I'll actually grab the code that we will be using itself and just throw that in here. Do not forget and be a moron and make sure to include your typedefs. And now I can explain through what all of this code does. So the first thing that we have is we have a type enum, and this is just all the different types of data that we can include inside. We have a nil type to let it know that nothing's been assigned. So by default, when we create a variant, it will always be set to be nil. And that's again here another thing that we'll want to add is that we specify that the type has to be nil at first, and also this type is private because we don't want to be able to have someone else set in their code what type it is when the type that is currently being interpreted is not being used. So the next thing that we have below is a union. Now unions, what they do is they take a group of data. So in this case, we have a bool, int, float, a general pointer, and a list of bytes. So that's why we have uint8. This is just a bunch of bytes that we can use. And what a union does is it shares the memory being used. So rather than having a bool, int, float, pointer, memory all laid out in one row, say as each individual type that we annex, we use a union instead because we want to be able to minimize how much data a variant transfers. We also have this align as 8. So the next thing that we have this clear function, and it is set as force inline. So what this will do is it effectively says this function, when we actually declare it, will be pasted in. So the definition we have here, all of this, whenever it's called in any function, the entire definition just gets effectively placed wherever it's being called at compile time. And what this function does is it takes an array of different booleans, and if the type that we have it currently set to needs to be freed, so if the data that we are using, say we are creating using an array, the array will have a pointer in it, and that pointer needs to be freed so that the data isn't being hogged by the memory and we're not overusing the amount of memory that we have. So, and that type will be set in this case to true. So when we look up to see if the type needs to be freed, then yeah, we'll call clear internals, and this just does all of the freeing for us. And it sets the type to nil to know that we've cleared out all of the data of this type. Then next, immediately below it, we have our clear internals type. So below this, we then have getting value as string. We have getting the return type. We have an equals operator, an equivalence operator not equal to operator, a hash compare function. Then we have a bunch of different operators Then we have a bunch of operator types when it comes to different data types. I'll get into these a little bit later when I'm explaining what they do. We have a whole bunch of constructors. We have an empty constructor and we have a deconstructor that by default just calls clear. So that's all of the functions we have here. Now, one thing I do want to touch on very briefly is that for the get value as string, we will probably, when we get around to creating our string type, change this from a const char to the actual string data type. And when we also create a string type, we'll be able to add in the functionality that actually makes this work rather than keeping it as is. Another thing to mention is this will not be all of the functions we use. There are going to be 1,000,000,001 that we need to use at some point along the line. This will be, again, as I've probably said for a couple other files, it will be a lot of additions when we need to be creating those additions as we go along. But that's this file pretty much explained. So let's just pop into here and create the variant.c++ file. And this will be our source file. We will include, of course, the variant.h. All right, I'm just going to go ahead and paste all of the definitions in, and we'll go through and explain each one as we go. So starting at the top, we just have our clear internals. This generally the layout that you'll see when it comes to variants is that it's a whole bunch of switch statements, which seems like it should be a little bit more advanced, but in reality there is not really a lot of easy ways of going around this. So by default, we'll be using a lot of switch statements because they're simply just the easiest way to iterate over each type. They are also the most efficient in this case rather than writing out 1,000,000 if-else loops because they at least look a little cleaner. So by starting off, we just have our clear internals function declaration. Again, because we have no types, they're all atomic types, as we would call them, which means that they don't hold any advanced data. They are just, booleans, integers, strings, and floats, so they don't need to be destroyed. They don't need to be freed because they are just normal data types. As for get value as string, we've only really implemented a couple of them so far. So here we have, const char variant get value as string. So at the moment, it can only really handle nils and booleans. So here for nil, because we just want to return the phrase null, we can just do that. Then here we just use a ternary operator to see if underscore data to underscore bool is true. If it is true, then we can return true. Otherwise, we return false. And in the case of int and float, because we haven't got any integer to string functions yet, there's nothing we can do. So by default, we return nothing. And by here, we also return nothing because it is, of course, an empty string and there's nothing we can handle with that. And again, the reason that we have default all the time is because here we have variant max. And while we normally use this to have things like, maxing out the size of an array, where you don't actually have to keep recalculating that value, it does mean that it does get included as something that we should be considering in an array. So by default, we always have to make sure that we have a default option so that we can ignore that warning for now. Then we move on to our operator equals. So I should probably go a little bit into detail on operator overloading as a concept, because this is probably the first point where we've actually seen in the series. So buckle in, because this is a pretty fun thing to go through. So operator overloading basically works like so. We have our default operators that you'll see, and I can explain it fairly easy. If you're plus, your minus, your divide, your multiply, you have your equals, your not equals to, your greater than or equal to. You can have shifting bits to the left, shifting bits to the right. All of these exist as operators that normally exist in different programs. And you've used them all the time, depending on your level of programming knowledge, because you always have to be using them. In C++, we have the ability to use operator overloading, which means that rather than using just the default atomic types, so say creating a variant or creating a normal integer and then swapping that over, you can now use assignment operators, so equals, to set custom classes to equal specific information rather than just assigning the classes in a direct manner. And you can do a whole bunch of cool things that would be above what the normal logic of a program may do. So in this case, as you can see, we just have a type, and we just make sure that the type is switched over so that we aren't keeping the residual type if we, of course, changing. So if we initially create a variable as an integer and then we start using floats, we want to make sure that the floats are being used and not the integers. Then we go through another switch statement of what the other type is. So if it's nil, then we just set our pointer to equal null pointer. This could be a problem if we start allocating memory, but I don't think I will be using the pointer type at all, really. We'll only be using it to create nullable types, which I will see about implementing at some point. Then we have a Boolean. So in this case, it will just take the data and assign it to whether it's the bool. Then we have the same case for an integer, same case for a float. And by default, we can't really assign anything if the operator doesn't exist. So our safe bet is just to break out of the application and ignore what's going on. The next operator we have below that is we have equivalence operators. So these are Booleans. If you're used to, say, in a statement saying, if X is equivalent to Y or Z is equivalent to 3, this is literally the same thing, but built into our type itself. So we don't have to do any differences in how the different functions may work. So both of these call a hash compare function, which generally speaking, I would normally use to hash a type. So we would turn it from being a normal variant into its residual types, which is what we do here. And we always make sure that we are comparing the different types. And it's fairly rudimentary so far because the only two types that we're using are Booleans, integers, floats, and nullable types. So we're fine by that. And again, by default, we will return false because we would assume that if the type isn't valid, then the operator is probably not equal. And it's not a good idea to be giving out types that we can't compare. So now we're moving on to the sort of the data type operators. What this means is, what this does is it takes a Boolean, so in our case, the type, and constructs it or returns the data type we're looking for as an operator. So rather than creating, plus equals, minus equals, divide equals, multiply equals functions for a variant, which we don't really need to do because most of the types that can be doing addition, multiplication, subtraction, and division already have these types inbuilt, we can just take it and say, okay, well, we're now looking at using simply the data types itself that we have inbuilt. So by default, if it's nil, nil is null pointer and null pointer is false, so we'll return false. Again, Boolean returns Boolean. Integer will turn if the integer is greater than 0. It returns true, otherwise it returns false. That's just default behavior, and the same thing for floats. And by default, we just say, okay, well, the data can't really return anything, so we're just going to return false anyway and assume that it hasn't been set. And we basically have the same thing going on for every operator. If it's quite literally the same thing over and over. We do have two different types of floats and doubles. I am realizing as I'm developing the engine ahead that it would be a good idea to have these types predetermined. So if we want to use floats, then we have that set up. But if we want to use doubles, we also need to make sure that there's a little bit of customizability there. So we will be looking at implementing something like this in the future. And again, all it does is it just typecasts if for floats if they are in a non-integer type. And this should happen the same for pretty much every type there. Now, the last little part of this code is our constructors. And we have a lot of constructors because we have a lot of data types. Another thing that's probably worth mentioning now, especially when it comes to these class constructors, is we have to use all of these individually because some types, like integers, aren't specified to be, signed or unsigned. It's just an integer type. So when we use these, we have to make sure that every single one's specified so that we don't end up having one generic type that it all goes through, and then the compiler has a little bit of a huff when it tries to figure out what's going on there, simply just because of how compiler logic works there. So that's why we have a whole bunch of these sort of like copy pasted, when in reality we could probably just use a uint32 for all of these, but it's fine. So we just make sure to set the type. And another thing you might notice here is that we don't specify int or uint because we're expecting the high level of the application to not really care whether it's unsigned or signed. The way we're storing it anyway as an integer is as a 64-bit integer, so unsigned doesn't really matter in this case. And there's not really a lot to talk about there because, again, these are all just assignment operators. Now that that's everything built there, I think it's probably worth making a little include and seeing if our variant type now works. Okay, so what we're going to do is we're just going to demonstrate that this is working by creating a variant called x, and we're going to make it equal to 3. Then we're just going to call our print function, and the number x is, and then we're going to say %i, and then we're going to typecast it to an int32 of x. So the reason behind this order of operations is that when we have x on its own, sometimes it just can't make the intelligent leap that it needs to be, in this case, an integer, because there's no operator saying, okay, well, we can turn it to a string or we can turn it to an integer, and it won't know that, initially speaking, because of the way it's expanded into a function. But this way, we can simply say to the compiler, okay, well, you need to make sure that it returns as a string. And because we have the operator type to say you can convert to an int32, then the numbers can do so. It is worth noting that the print macros will be going away. I've done a fair amount of development, and I've changed how we actually access our print functions. So these logging macros won't be used everywhere as they were initially. But that's enough out of that the way. We're just going to hit Control-Shift-B to compile, close the terminal, run the code, and what we'll see is that we get our previous debug messages, and we also get it saying that the number is 3. So that means everything is now working, and that's pretty much the variant type set up. There are a couple things that aren't quite working, like operators, so doing our plus equals, minus equals, divide equals, times equals, and unfortunately I haven't really gotten to the point where I've been using the variant enough for this to be an issue. We will be revisiting the entire type of course, and we will be making sure that everything does work. But for the most part, this is how we'll leave it for now. But anyway, I do hope that you enjoyed this video. In the next episode, we should be taking a look at vectors and arrays. And I believe that we will also be doing a little bit, I think the start of that video, we'll also be looking at a little bit of memory management and sort of going over memory management basics, because that needs to be something that is addressed, of course. And I think they're best to do as one overall video, because the two will make a lot more sense when they're combined. But anyway, I hope you enjoyed, and I will see you guys in the very next video. Goodbye.